Welcome to clickmyproject.com. Dynamic multi-level priority packet scheduling scheme for wireless sensor network. We propose a dynamic multi-level priority packet scheduling scheme. In the proposed scheme, each node expects those at the last level of the virtual hierarchy in the zone-based topology of the wireless sensor network has three levels of priority queues. Real-time packets are placed in the highest priority queue and can preempt the data packets in other queues. Non-real-time packets are placed into two other queues based on a certain threshold of their estimated processing time. Leaf nodes have two queues for real-time and non-real-time data packets since they do not receive data from other nodes and thus reduce end-to-end delay. We evaluate the performance of the proposed DMP dynamic multi-level priority packet scheduling scheme through simulation for real-time and non-real-time data. Simulation results illustrate that DMP dynamic multi-level packet scheduling scheme outperforms conventional scheme in terms of average data waiting time and end-to-end delay. In the proposed scheme, queue size differs based on the application requirements. Since the preemptive priority scheduling inquires overhead due to the context storage and the switching in resource-constrained sensor network, the size of the ready queue for preemptive priority schedulers is expected to be smaller than that of the preemptible priority schedulers. On the other hand, non-real-time packets that arrive from the sensor nodes at lower level are placed in the preemptible priority queue. The proposed scheduling scheme assumes that nodes are virtually organized following a hierarchical structure. Nodes that are at the same hop distance from the base station are considered to be located at the same level. Data packets of nodes at different levels are processed using the time division multiple access scheme. They are rather calculated based on the data sensing period, data transmission rate and CPU speed. They are increased as the level progress through base station. However, if there is any real-time or emergency response data at a particular level, the time required to transmit that the data will be short and will not increase at the upper level since there is no data creation. The remaining time of a time slots of a node at a particular level will be used to process data packets at other queues. This is our flow of our project. It consists of 7 blocks: FCFS, multi-level queue priority, real-time packets, non-real-time queue, and non-real-time that queue, and average waiting time, and it's a performance evaluation. In FCFS, first come first serve scheduler that process data packets in the order of their arrival time and thus require a lot of time to deliver to a relevant base station. However, to be meaningful, sensed data have to reach the base station within the specific time period or before the expiration of the deadline. Additionally, real-time emergency data should be delivered to base station with the shortest possible end-to-end delay. Hence, intermediate nodes require changing the delivery order of the data packets in their ready queue based on their importance. The next one is multi-level queue priority. In multi-level queue priority, queues in the multi-level queue scheduling algorithms. Moreover, these algorithms are not dynamic to be changing requirements of wireless sensor network applications since their scheduling policies are predetermined. In each node, expect those at the last level of the virtual hierarchy in the zone-based topology of wireless sensor network has three levels of the priority queues. Real-time packets are placed into the highest priority queue and can preempt the data packets in other queues. Non-real-time packets are placed into two other queues based on a certain threshold of their estimated processing time. The next one is real-time priority 1 queue data. Let us assume that a node X residing at level K is sensing at a real-time emergency event, for example fire detection. This node transmits the emergency priority 1 data to base station through the level 1 intermediate levels. We consider the following scenario whereby every time a real-time data packet reaches a neighboring active node at an upper level, a non-real-time lower priority data is being processed at that node. Hence, data delivery at Y is preempted to send the real-time data. The next one is non-real-time priority to queue data. Task at P at Q can be preempted by real-time data. Taking the scenario of when a real-time task is sensed at a node 11 and it is forwarded to base station through the relay nodes 9, 6 and 2. It should be observed that tasks are available at the peer to queue at nodes 9, 6 and 2. Since one real-time task is available at the peer 1 queue of nodes 9, 6 and 2, real-time task will be processed and transmitted during the time slot of nodes 9, 6 and 2. The remaining data are wait until the PR1 queue is delivered. The non-real data PR3 queue data are arrived at the PR3 queue, and it can be printed by both PR1 data and PRQ data. Until PR1 and PR2 deliver, it has to wait. In our next block is average waiting time. In average waiting time, we can calculate the overall waiting time of PR1 queue data and PRQ data and PR3 queue data. In performance evaluation, we calculate the overall average waiting time and end-to-end delay for the overall system of our dynamic multi-level periodic queue scheduling.